Okay, so homework 2 is up, uploaded on KLMS. Hopefully you received the email. And it's due October 19th. Hopefully that's enough time. So I added a bit more because there's this Korean Thanksgiving break. You don't want to suffer. I don't know if you're going to enjoy, like, wow, I have this homework over the Thanksgiving. I don't have to talk to uncles. And anyway, so it's October 19th, and enjoy, and you can again submit to TA. I don't know, on KLMS or email, up to you. Any questions so far? So last time we talked about space-time symmetries, right? So we talked about Noether theorem, the implications of a continuous symmetry at the level of action or classical limit. And we talked about translation and Lorentz transformation, and we derived Noether's current. And then we sort of looked into a bit, right, to make sense of that, right? Whether it makes sense, that expression is what you would have expected based on the physics intuition or not. That's what we did. Today, we will spend time to talk about internal symmetries, which plays an absolutely crucial role in the development of not only quantum field theory, but also particle physics, cosmology, that's matter physics, presumably also in statistical physics, and so on. So we will spend some time today. But before I jump in, if there are any questions, I would be happy to answer. Yes?
About the energy momentum answer.
Yes.
We can obtain that by the variation of metric.
True.
But what's the relation between like the variation of metric and the small translation?
Okay, good. So that will be the homework problem. Thanks for right. So you're asking whether you will get a canonical version or already I forgot what was it? Some Rosenfeld version or Coleman thing. I would make it a homework problem, but although that technique is useful in general, that is fully justified. Fully, I don't know. When you can treat gravity as a perturbation and so on. But still, even if we talk about just quantum field theory, flat space and time, you can nevertheless turn on certain, because you have to do the functional derivative with respect to metric to derive that. Still, it is a valid technique. I don't know the answer off the top of my head. I would guess it will be canonical version, but you will find out in homework 3. Okay? Okay, any other questions? Okay, good. So let's talk about it. Last time there was a question. So far we've been integrating, in order to get a charge, right? So far we talked about in the sense of integrating zeroth component of Noether current on a time slice, right? And there was a question whether that's the only way to do it, and I said roughly that no, you can actually do much more covariant way. Now, I will just make a short comment about this part, and then I'll just move on to the internal symmetry. So recall Noether's current is given by and then F. Right? So that's what we talked about so far. And what I want to talk about is that first I want to make a somewhat blunt statement about the quantum version of the statement. Okay? And then we will therefore start talking about not just the charge, but charge operator that you can have on your Hilbert space. You can act on actual quantum field operator. Okay, and then so on and so forth. So that's when this sort of statement becomes somewhat more useful. So far what we talked about was that there's a classical action. So here action represents that we are talking about physics at the classical limit. And then if we have a symmetry, here just focusing on continuous symmetry, then the statement was this. So there exists a conserved current. So that's the classical statement. And eventually we will be talking about the quantum theory, quantum field theory, by quantizing this theory. And then here, there's an object that you will find useful at some point. You don't have to know at this point, but this J is very different from that J. But that looks exactly the same. So, J. I solved the problem. So, eventually we will talk about what is known as partition function or generating functional. There's action appearing in this form. And then for a field that you have, you can couple to what is known as a classical source field. Don't worry too much about it. So, and then you can compute a lot of quantum correlation functions out of that. Now, what I want to say is that therefore, you can now, once you quantize your quantum field, then this will also appear to be an operator made out of a quantum field, right? So this is made out of a field. And then once you quantize those, you will get actually quantized version of the current. So you will get quantum operator, right? And then you can show that you can take that, let me just write that carefully, quantum operator at t, a given time slice, and you can act on your quantized field, and then you will find out that you should get something like this. In other words, here commutators sort of represent the action of this quantum operator, and it will actually perform up to this minus I factor, do an infinitesimal transformation. Okay? Now, how do we see that? Well, so I was gonna say the given quantum theory, so then if you have again, continuous symmetry. So here we got Noether's theorem. Okay? And then here you get what is known as word identity. Now, this is sort of a spoiler. So I'm not actually lecturing on the topic of a word identity and how to derive them or not, but I'm just gonna state the identity quickly and just sort of give some word why that kind of expression you would expect. And I'll just use that to sort of derive this expression. And then I move on to discuss, whether we can generalize notion of integrating over the spatial slice. Okay, so that's my point. So this is a consequence of a word identity. So what is word identity? So you had a classical conservation equation. So once you quantize, so sort of you might expect to see something like a quantum version of the equation. Something like that. Right? Naively. So instead, once you can use the machinery of path integral and so on, you will see that first of all, in quantized theory, the object you're interested in is sort of a expectation value. That kind of thing. But in particular, as we will develop soon, okay, in maybe 1.5 weeks or so, we will be interested in the object what's known as a time-ordered vacuum expectation value. So let me define what time ordering means here. So suppose you had a two-point function, just to simplify, we can generalize that notion. This is defined to be time-ordered. So if time of x is larger than y, you have to order according to time. So you have to write x later than y. Later than that sense. But if time over y is larger than x, then again you have to order according to the time. So you have to write y after the action of x. Okay, that's literally what it means to be time ordering. And we will see that eventually, once we start developing a machinery of perturbation theory, this thing will just appear automatically as a necessary gradient. We'll see that. Don't worry about it. But now I will state actual statement according to or corresponding to this quantum version. Then the statement is that we will kind of look at a correlation function, time-ordered correlation function within a quantum operator at x with some other insertions of operators. For instance, by y and so on and so forth. And this, for instance, one of the objects which are charged under whatever the symmetry we are talking about. Otherwise, it's completely irrelevant. Okay? So I certainly want to look at the current because I'm interested in what's the implication of having a symmetry current. And obviously I want to insert some operator which is charged under that symmetry, otherwise it is completely decoupled. And then the relevant statement is that what would happen if I take the divergence of that correlation function. This correlation function, if you properly compute, it's just a gigantic function of x, y, z, and so on. So you can just take a derivative with respect to on that particular function, which you use it whole entire quantum machinery to compute it. But once you compute it successfully, as you will learn, then you can just ask, what is the divergence, right? And then the statement of a word identity is that you actually get minus, if you have that, well, I should just d. Oh, I forgot the delta. Sorry. Equal to minus my delta x minus. So by the way, this is derivative with respect to x because I'm having a curve at x. So I'm interested in asking this question, and then time ordered correlation function of d. So this is the same. Let's see if this is what you expect. You say, no, I wanted to see 0, and you gave me some complicated expression. So definitely that's not what I was expecting. So suppose you didn't have any of that, right? Then clearly you get 0 on the right hand side. If you expect from the quantum version. Now if you insert a some charged operator, unless the location of current you inserted overlap with the location of a charged object, meaning this is enforced, right? If this is not the case, again, you get the 0. That makes sense, right? There's a beautiful, nice conserved current operator, charged object. If they don't overlap each other, okay, they don't interfere with each other, you just get 0, as you'd expect from this system, okay? Now, but then only if the charged object sort of start crossing the location of a conserved current operator, it knows about it, and what it does as it crosses it, it actually performs the infinitesimal transformation. Okay, so that is this quantum word identity statement. I'm not deriving it. I'm telling you that you can actually derive it, or you will learn once you use this machinery. Okay. What I wanted to now tell you briefly is that if I accept this as an expression, given expression. So basically, therefore, one first statement is that there's a quantum version of a classical Noether's theorem, which is based upon a correlation function. The symmetry implications of symmetry on the correlation function, rather than just action, and that's just word identity. And then now what I'm gonna do is that I'm just gonna literally use it, and then just derive this expression. Okay? So let's just do that. So let's just take this as granted. And then next, what we're going to do is that we're going to actually derive this quantity. In order to do that, because this is defined in terms of a j of 0, and then I will have to integrate over the space, let's take that. So, and then let me just consider one insertion. So time derivative. Okay, and then this is time order. So theta of x0 minus y0, then j0 x, y. The theta of y0 minus y0, y x. Okay. We are doing good. Okay, so, there's this complicated theta. Let's worry about that later. Let's first hit here, hit here. Okay? Are you with me? Okay. Actually, you know what? Let me just start out with the full version. Why not? Eventually we will constrain to do that, but why not? Let's just start with full version. So then I first get this. And then I get second term. right? So I just literally acted derivative. Remember, this is derivative of the x, so it doesn't know any y. So just pass through that. Now I have to worry about the theta. Since this is only a function of a zeroth component, obviously when I do it, you don't need to fix out the zeroth component, right? Okay. So I'm going to continue to write here. So that is, the first I hit it, I get a delta of x0 minus y0. But when I do that, I have to use only zeroth component, which means that I only single out j0 components. Now, next time if I hit here, because it's minus sign, I get minus delta. The delta function is even already flipped forward. And then I get phi of y equals x. Right? So I can now just rewrite using the definition of time-ordered correlation function. So that first one is basically time-ordered correlation function of divergence of current operator, even though at some point I already forgot to put that. Good to know. Okay, so that's summary of the first piece. And then the second piece, I have a delta of x0 minus y0. Then what do I have? This is that minus that as operator statement. What is that? That is a j0, x, and that, right? Now, we're almost there. So this is a quantum version of a divergence, right? I was asking divergence of correlation function. This is literally divergence of quantum operator. And then, for instance, if you have actual expression, do it. And then if you evolve equations, motion, whatever, this is just identical operator statement. Okay? So it appears that the correlation function not at the level of operator. Operator, you can literally just compute it, what that looks like. So that's 0. So therefore, we arrive at the fact that this should be equal to, according to word identity, this. Okay? Now, I want to get the expression in terms of charge. So what do I do? So take this, and then take this, and then what do? You integrate over space to get this, right, as an operator now. So if you integrate over the space for now, then let's first look at this side. I get x0 minus y0, and then what do you get? Quantum operator at t, and then phi of y. So that's left hand side. And then right hand side, you again split the delta function that includes this piece. But then the rest, if you integrate, what do you get? Well, you just eat up the delta function. So you have to select your integral over x. So you get basically so point by point at time. So if you get an identity that I was claiming to be the case. Okay? Good. So what do we learn? Also, what is the geometrical picture of what just happened in this algebraic equations? So say this is the time fluctuation, okay? And then you can piece some time, another time, there's a time ordering. If you have an insertion of a charged operator, by what in this example, right? You were looking at the difference between the case where time of j is later, time of j is before, earlier. So you're looking at, and then you integrate over the space. So you have a surface, integrate over surface. There was a j0 component, and later, and then you sandwich together. Okay? And this literally completes the commutator. And then once you do that, what you do is, this guy will go through a transformation, infinitesimal transformation. Okay, good. So now I can state what I sort of wanted to state. So now we can actually define a charge operator at a given time. But let's just write it as this. We write as a certain time fluctuation like this picture, and then we integrate this. However, the statement is that, in fact, you can actually just integrate over any three-dimensional closed manifold. And then you can integrate over this. So now, I don't know if you're going to upset it. So let me just put first this. Now, I'm about to write a more geometric expression. So that means that I'm just actually integrating over, let me just plane. So what is that? So current has a single index, right? This is Lorentz index, there's a conservation, and then you can think of this as actually coming from a one form object, one of the geometrical object known as a one form, differential forms. Okay? And then this Hachi dual, roughly speaking, so in this of that is actually, roughly speaking, taking mu plus sigma of, so this converts to one form to three form. How? I'm just gonna state that, roughly speaking, contracting with that. Up to metric, you have to put some metric factor, but I'm not worrying too much about the detail. So basically, therefore, what I mean by that is that I'm integrating over the three surface. Right? Which means that you want to integrate over the three form. If you ever had any chance to hear about anything about the differential form, how many did I say? So there's a three-dimensional manifold, you want to integrate the three form, define on that. Okay? And then, so therefore you're reading off the three spatial components of this thing, but there's a Hachi dual that comes from, you invert, so you have a four component, you want to look at the three spatial component, Hachi dual selects out basically the remaining. Right? So there's zero components. So you can actually check explicitly. So what I want to say is that here I have not done anything fancy. All I said was that, okay, how about I'm just going to rewrite this in terms of more fancy differential form language, first of all. Okay? If you don't get it, it's okay. Okay, this is will never be tested. Although I don't know if there will be any test at all. We'll see. And then I can use this expression to show you that actually you don't have to pick a specific type of division slice. You can integrate over any three-dimensional manifold. So how do we see that? So let's pick a charged object here, phi of y. Okay. And as that picture suggested, eventually in a spatial infinity that are connected, so basically you can wrap it up to form a closed surface like that. So if you wish, this is a given time slice, given a local operator, I'm surrounding with the shell. Okay. So let me call, okay, so this is looks like a two-dimensional picture, let me call this sigma 3. Okay. And then let me deform this arbitrarily but smoothly to another three-dimensional surface, sigma 3 prime. Okay? And then what I wanted to show is that this quantum operator defined with sigma 3 prime is the same as that thing defined on sigma 3 itself. One catch is that when I deform this surface to that surface, I have not passed through or crossed any charged object inserted in between. Okay? So if I have one charged object here, another one there, I'm free to deform any way I want, okay? Except the fact that I don't want to cross the second one, because then I have to go through another word identity, okay, and transform it. So let's just check this. So this is given by sigma 3 prime star j1 minus sigma 3 star j1. And then you notice that there's this volume. Let me call that volume to be four-dimensional volume hat, whose boundary is that and that. Okay? So this can be written as a sigma 4 hat integral using the Stokes theorem d star j hat 1. And it turns out that this is exactly basically the same as looking at this up to, I just have to put dx, dy, x, dz, x, dy. Okay? This is the full form with that component. So long as I am dealing with a current operator which is countered in this sense, then this is identically 0, showing that this operator, that operator is the exact same physical implications. So in fancy way, you might say all of a sudden, boom, we all of a sudden talk about this differential from where they come from. Okay, it will go away right after. Don't worry too much about it. But I just wanted to deliver a message that in modern perspective, symmetry means that you have a certain operator which is topological in this sense. So the meaning doesn't change if you make a small continuous deformation. And you just don't cross the charged objects. Okay? Hence, in modern version, once I have a charge operator, then I can actually construct a symmetry operator. Like that performs the finite transformation. So we call a symmetry operator, or sometimes called defect, symmetry defect operator. So let me write it as a U. Okay? And then if I want to talk about certain symmetry that is defined under sigma 3, in this example, I can exponentiate that with some parameter alpha. That will be my operator defined in the Hilbert space that performs a certain finite transformation using a charge or generator.
What is the Hilbert space?
What is the Hilbert space in this case?
Yeah, because Hilbert space is defined on a time slide, but you are not considering the equal time foliation, so we cannot define the
Okay, so that's probably why I put the defect there too. Because here, when I say this, I'm not particularly, taking a Minkowski picture, and there's a certain notion of time, and the rest is the space, and then foliating it. In a sense, secretly or implicitly, I already went on to the Euclidean space and time, so there's not much of a time versus space. I'm not worrying too much about it. So in that case, I can define this regardless of the direction of time versus space. But if you like, this thing you can foliate according to whatever direction you want to choose, if you like. But at the very least, you can just take a classical minimal picture of this sort. Okay.
I think at least you must choose sigma 3 as complex surface because
Yes, that's right.
because you use the Stuckus theorem.
Okay, I don't think that contradicts with anything. I'm sorry. Yes. Suppose I do that.
So if you select the foliation as the typical infinite surface, which is not complex, then over such analysis.
Sorry. If that is your concern, I can solve that very quickly. I'm trying to understand so if I add a point, right? This is not compact. I solve that problem. Okay, and this is costless. Well, you made a lot of cost for that, at least for this discussion. Now, I'm not worrying about R3 versus S3 problem here. Okay. So now, given this charge operator, which is a generator of an infinitesimal transformation, I can exponentiate to get now finite transformation operator, which is symmetry operator or symmetry defect operator. Okay, that you have. And in modern perspective, of the symmetry is that if there exists, okay, if you find a topological, in this sense, topological operator that acts on your theory non-trivially, meaning at least it does something. In this example, it will perform a transformation of this certain operator of your theory. Then you know there exists a symmetry in your theory. Okay? So let me state that again. So in modern perspective, the definition of symmetry can be stated as the existence of a non-trivial topological operator, non-trivial topological symmetry operator, symmetry defect operator, that acts non-trivially on your theory. Okay, the second part should be almost contentless in a sense. If it doesn't act at all on your theory, why would you even consider that? I can write down million random operator, beautifully topological, does nothing to me. Okay, what's the point of it? Okay, hence, okay, anyway, so I just wanted to phrase a bit of a modern perspective. And last statement I want to say all of this line is that in this example, the dimensionality of the symmetry operator is a 3-dimension, right? When we talk about 4-dimensional physics, okay? Turns out that that case, that acts on the local operator, as we talked about so far, and that is an example of what is known as the zero-form symmetry. And it acts on the local zero-dimensional object or particle. In modern days, we know that there exists a topological operator whose dimension is not necessarily like 3 in the example of 4-dimensional space and time, or in a fancy way, codimension 1 operator. You can have a operator which, for instance, 2-dimensional or 1-dimensional in 4-dimensional space and time. And there, then we know that there's an object which is not local operator, but extended object like a string, a line, or a surface. So in that case, we are talking about the symmetry that acts on the extended object known as the higher form symmetry. I didn't mean to open this box, but anyway, so now you know there are more broad notion of symmetries. So long as you have a technique to handle the existence of topological operators, and so on, you can talk about extended object as well, not just a local one operator. Okay, so that's all I wanted to say about the first part. Okay, good. Let's move on. Any questions? Yes.
What I need is the identity or expectation value. But what you raised is there is no for bracket.
Wasn't? Oh, well, I stated the word identity as a divergence of a time order expectation value with a current operator, current insertion, and then some other operator inserted, right? Equal to minus I delta and then impedance. So it is a word identity expressed strictly in terms of expectation value, time order correlation function.
So we can have another term in terms of operator expression, like A expectation value of A.
Without that.
Yeah.
Oh, okay, good. So let me just clarify this one. Okay, so what was here was what was there was something like this is equal to this, right, up to delta. And then if you had the insertion of any other stuff, that equality is still valid, modulo some conditions, okay? Which means that sounds like this, I can just write it as Q phi minus D as an operator identity, by which I mean if I insert this in any correlation function, I get equality by inserting that in that place. So that's the sense we can write, starting from this correlation function statement, which is valid for any other insertions of other operators. Okay, modulo whether they are charged or not, or not. There's again specification. I can extract what is known as an operator statement or equation, which you have to understand as the fact that you can insert this in any other operators, and then still the equality holds. Does that answer your question?
Do we say that derivation of that operator?
Well, so up to this point, there's no like subtle, right? It's just streamlined derivation. And then, so long as if I know that this equality holds in the presence of other, say uncharged operator under Q, any set of operator, sounds like
in the case of uncharged operator,
yeah,
it's always true.
Yeah.
But if we insert any
charged operator, then this equation just gets generalized. Okay, which I didn't consider that, but now it will be sum over variations of that operator with the delta function properly. So there's a general version of that, and again, you can extract that as a generalized version of operator equation, even if there's a chain of other charged operators. So one can derive a word identity in full generality. Any other question? Okay, so let's move on to internal symmetry. So it's okay you forget about the last 30 minutes. Hello, welcome to the lecture. So let's talk about internal symmetry. So internal symmetry, as opposed to being a space-time symmetry, okay. But I'm gonna say too much subtlety part. Okay. So let's first look at the scalar field. This, as we talked about. And first of all, let's think a little bit about what this is doing. What is that? So one way to think about that is that this is a mapping from, for instance, space and time. So if you give me space and time data, and it will spit out the field operator value, right? And if I consider only one real scalar, it can be either R, or if it is if this phi wrap around a circle space, it can be S, and so on, right? So this can be viewed as a map from the space and time to whatever the geometry or topology of the field space itself. So just to illustrate the point, let's consider another example. So let's take a two field. Okay, so now I have a field that consists of two components. Both of them I'm taking to be real. Then what? So again, this can be viewed as a mapping from R3,1 to now there's internal space, right? Which looks like two-dimensional. So I don't know until I specify what that is. We wouldn't know yet, but it's something like this, right? To circle or to torus or something like that. You can keep going. So what if I have a phi 1 to phi n? Again, you just keep going. This to some n-dimensional space. Some m-dimensional space, which we don't know yet. As yet, for now. Okay? Now, internal symmetry, as opposed to being a space-time symmetry, right, is some symmetry that acts on this field space, internal field space. Okay? So let's take a concrete example to illustrate the point. So I'm just gonna, this part of the lecture, I'm just gonna take a whole bunch of examples, okay, go through that and how to understand that, how to relate them, and so on and so forth. So let's take a example number 1. So here, let me take a phi, as one of the examples I already talked about, consists of two components, and both 1 and 2 are real scalar. And suppose I give you the following action, a Lagrangian. So I have, would you be okay if I write this way? Or you're just like, what are you doing? Are you okay? Okay. Would it be better to write it as, because I'm bothered by this, right? Are you too? You're not? Okay. You're optimistic. Certainly. But I'm lazy to erase that. So, okay. Right? So here is a theory that consists of two real scalars. And we derive that Lagrangian. Now, if so there's a degeneracy of the masses, then I can rewrite this section in terms, and then let me just write that as this m squared. I can use vector notation to rewrite my Lagrangian as half. Can I do this? Right? We can write this way. Okay? And transpose, because I'm talking about the real scalar. Now, let's ask. Consider now transformation of this thing. Let me put a labeling for now. Now I'm raising it. It's okay. Life is okay. So let's consider some, sending some so this is a transformed field, this field, and then this is a linear combination of original field. Okay, so A and B runs 1 and 2. Is that clear what I'm writing? This is a vector transformation. And then let's ask, is there any M that I can find that leads action invariant? That's the question here. Now, one condition though is that this matrix, which is 2 by 2 matrix, right, has to have a real entry. Is that clear? Right? Because I'm taking a real scalar field, I'm sending that to transform the field, and it has to stay as a real scalar field. Okay? So I cannot have complex entries. That's one condition, but let's actually check. The Lagrange will transform as, in again, matrix notation, M transpose. Now I'm just writing as a vector notation, minus Are you with me? Okay. So therefore, I want to find the symmetry, and that corresponds to solution where this factor is a 2 by 2 identity matrix. Right? So therefore, in the limit where there's the exact degeneracy of the mass parameter of the theory, we find out that there exists this symmetry, 2 by 2, this matrix, and that thing has a name. What is that? Two-dimensional orthogonal group. Okay? Now, we can split this O2 into a two part. So this thing has a 2 patches. Okay? So first of all, we can talk about SO2. So let me first derive it, why we have to talk about this. So let's take a determinant of this thing. So determinant of m dagger m, which is determinant of m squared. And this is this identity matrix, so it is a 1. Which means that this is a real entry, as we talked about, which means that determinant of m is either plus minus 1, right? So there are 2 patches. I can look at a determinant of plus m, and that corresponds to SO2 part of this O2. Okay? We talked about similar thing in the context of Lorentz group. This is proper or special, whichever way you want to say. And then there's a minus sign. But then you can just access to minus 1. Remember, all these entries, elements are connected to the identity in a smooth way, as we talked about. This one's not. So you can access the other page by taking SO2 and then considering 1 discrete transformations. Very similar. In that case, let's just take this discrete transformation. It would be 1, 0, 0, minus 1. Okay, certainly this has a determinant of minus 1. Okay? And so I will call this to be a reflection in field space. So it's as if you pick a phi 1, phi 2 as a 2 coordinate in your field space, right? It's just a flip in one direction, like 2 direction. This is reflection. You might say, oh, that's too much discrimination for phi 2 against the phi 1. You can pick the other way around, right? That's related by minus 1 minus shift, right? This is an element of SO2. So you can democratically treat it, but let me pick this as a 1 line choice. All right? So, good. Okay, so this theory has therefore O2 symmetry. Let's focus on SO2 for a while. Eventually, we will hammer this reflection part in the context of charge condition. So let's for a while study SO2 part. what did you do? By now, you learn all this Lagrangian and then canonical, quantization and all that, right? So you learn all these machineries. So at the very least, once somebody tells you this much information, you should just go through a process almost no-brainer. What did you do? Well, I just learned a symmetry transformation that leaves Lagrangian exactly invariant rather than being shifted by the total divergence. So what should you do? First, you want to derive Noether's current, right? And good news for you, this is 0. Exactly 0. So let's talk about this. So the only thing we need to do is that we need to figure out this thing. Okay? So I'm talking about this, so basically I need to figure out a infinitesimal transformation. 1, 2, prime, prime. It's like SU2 rotation. Well, it's not like SU2 rotation. It is the SU2 rotation I'm talking about. It is like two-dimensional world and you're just doing the rotation. So it is a cosine alpha, sine alpha, phi 1, phi 2. Right? So if I take the infinitesimal limit, so I'm looking at infinitesimal transformation, d phi 1, by looking at this original 1 plus epsilon times phi 2. So I'm stripping off the epsilon, so it goes to phi 2. And then the way phi 2 changes is that original 1 plus minus epsilon phi 1. That's minus phi 1. So let me just recap this as transformation of A is epsilon AB phi B. Okay? So, what is Noether's current now? I had action here, Lagrangian here, as you can see. So if you do this, you get the derivative of phi 1 by looking at the phi 1 part, and then the variations, that's phi 2. Minus, well, that minus comes from this minus, phi 2, and then phi 1. Yes? Okay, what do you want to do next? You want to check it? Let's do it. So that I hit this, which gives me a box of phi 1, phi 2. Let's hit that one to there also. That gives me box of phi 2, phi 1. Okay, now let's hit this derivative there. That gives you box of, so now box, derivative of phi 1, phi 2. And if you do it here, you get minus the same one. Right? Second line cancels. First line gives me, using, this is crucial, using classical equations of motion. Remember, conservation of current, when we derive the Noether theorem, is based off evaluating equations of motion, right? You have to get rid of the product term. That's what I'm doing here. So m1 squared minus m2 squared, if I do it, well, phi 1, phi 2. So as we assume, right, if there is a mass degeneracy, there's a conservation current, you have to see. There's a consistent check. Okay. Now, let me say more physics about it. Now you notice that, phi dagger, transpose, not dagger, it looks dagger, transpose is O2 invariant. Right? If you perform it literally invariant. Which means that you can take a Lagrangian and promote it to what is the fancy notation for promotion? Promote it. Is that enough? Should. Can I now, with this confused? Who's been sleeping? Now you might say, what is L0? You know what I'm doing? So let me call the quadratic action to be L0. Is that okay with you? Are you? We'll see. Let's see if there's a question. What was L0 again? So let me just put L0, and then let me add any like random term, which is some polynomial of this. And let me just put some coefficient ahead. Okay? And since I'm already at quadratic action, let me start adding this from the 3 to whatever you want. And still, any of this doesn't break any symmetry. And this theory has the exact same symmetry as before. Yes? So L, so let me call that L1. L1 is still O2 invariant. However, now if I start adding, so on the other hand, if I now do this, for instance, this, and then, for instance, if I start adding terms like, phi1 to the fourth or phi2 to the fourth separately, phi1 cube, phi2, phi1, phi2 cube, phi1 cube square, and so on. Now you see that these terms does not respect the symmetry. Yes? So they break explicitly the O2 symmetry that we're talking about. And there's a fancy way of saying this. Suppose there is a parameter in front, so coupling constant from each of these parameters of your theory. Then you can say that in the limit where if you demand the O2 invariance, what do you say? Now almost trivially, those parameter has to be 0. So you understand for the, hopefully not for the first time, that there's a reason, this is a symmetry reason to understand why certain parameters of the physics theory is identically 0. Right? If you impose a symmetry, some of the parameter goes to 0 identically. Okay? Now, when this is not the case, meaning you somehow found, but either by measurement or by calculation, some quantity turns out to be completely 0, yet you don't understand any symmetry associated with it. Right? Whenever we have this situation, either high energy physics, formal physics, or condensed matter, any other branch, we are in the moment of a puzzle, right? Oh, why is that? Okay? Most of the time, there's a deep reason behind this. And the task as a theorist or physicist is first to look for, are there any symmetry that we've been missing to understand either the exact zeroness or smallness of the parameter? If not, you work harder to understand why. Good. Anyway, so let's keep moving on. Okay, so now we understand, we did our basic study. So now let's study that for free field theory. Okay? For free theory, meaning I don't add any of them. I'm just playing with only L0. Okay? So then, as you know, you can write your field as mode extension alpha A. Is this better to write here now? Too late? Screw that. Okay. Alpha E. Right? You cannot do the mode extension. And then you can ask, and then each of these alpha diagrams satisfy commutation relations that you would expect for free theory. Then you can actually derive. I'm not gonna do it for you. So I'm just so far just doing literally no-brainer thing. Construct it, and then I'm just gonna compute it. Okay? And you can compute it, and you should find out that this is equal to so in your homework problem, you will ask to just derive it. You see, again, no-brainer, just to plug in this expression, and then use the expression for the Noether's current, derive it. Okay, so for no-brainer, now you have to think, does this expression make sense? What does that mean? So let's first do literal interpretation of what this expression is. Up to these factors of I, at each momentum site in the Fock space, what this does is that if you see any phi1 particle, you destroy that, instead replace with a 2 particle. If you see particle 2, you destroy that, you create the number 1, first particle, and 1 particle with the minus sign. And that was sort of what was happening. If you recall, this was, okay, I'm trying to be consistent for things to be fair. Okay, this was what was happening, right? We must say, oh, what about the minus sign and here? Okay, I'm not very happy. Well, so therefore, one thing you can check explicitly is that you can actually check, for instance, now this is actually already quantum operator, right? I already quantized the field, and then you see this creation knowledge and operators. This is quantum operator. So once you have a quantum operator, remember, you can check this. And the word identity, the general statement I said before, was that you should get this, right? But in this particular example, this is for SO2. Therefore, what you should get is minus I epsilon AB phi B. So now I encourage you to go ahead and just first derive this, and then just literally evaluate that and confirm that you actually get this correct. Okay? So far, check, everything is good. And in addition to that, you should be able to check that if this is a symmetry, remember, if this is a symmetry, so if SO2 or O2 is actually a symmetry, what do you expect quantum mechanically? You expect that this thing actually commute with Hamiltonian, and you expect that this actually commute with a momentum operator. The first you might say, yes, of course that makes sense. What about the second one, right? That just means that any momentum eigenstate will also be, eigenstate of this internal symmetry. Another way of seeing these two statements is that you can just combine them together and saying that there is this property, right? What it means is that this thing is completely independent from space-time translation. So this is a notion that I'm actually talking about, not part of the space-time transformation, but actually just the completely factorized, decomposed internal symmetry transformation. Is that clear? Okay? Remember, there's a set of a space-time symmetry. There's a translation, there's a Lorentz. They were not completely free, right? They had a non-trivial commutation relations. Lorentz algebra, Poincare algebra. Now here, this as being one example of internal symmetry that only acts on the field space, right? They have to just commute. Okay, so then again, you can check whether that is fulfilled. Any questions? Okay, so now I'm gonna do one exercise which will be useful. As we just talked about, this and that 2 points. So this tells me how original basis of field in terms of phi 1, phi 2 transform under this symmetry. Right? Now, this tells me that this is actually a symmetry of quantum mechanics or quantum physics. And you learn that whenever you have a maximal set of mutually commuting operators, right? You should be able to find a eigenstate which is eigenvector of every one of those mutually commuting operators. And somehow what we found is that this as a field rather than the quantum state is not an eigenstate or eigenfield of a Q, right? Because it's not eigen because it switches to something else. And you might wonder, can I diagonalize them? Right? Can I diagonalize this Q in terms of quantum field? So let's diagonalize Q. Yes, old habit, damn it. Okay, so let's diagonalize Q. So to do that, first of all, you can take like some more mathematical path and actually try to derive the diagonalization procedure. Let me just propose a solution and check it. Okay? So here I'm gonna do the following. Did I already use the capital phi? I did. That was, so let me use verify. So let me define this as a phi1, phi2. Okay, why there is so much square root 2? And then, okay, actually, you know what? I mean, this is correct. I'm not erasing something is incorrect. But let me pretend that I'm going to write this way. So I'm going to define a B operator, creation annihilation operator, in terms of A, what did I say? 1. A2, square root 2. Well, momentum is there. Let me suppress that. Would you allow? You wouldn't. Would you? Yeah, it's chemically the same. Until you say it. Okay? You're not what I'm doing, hopefully. So B dagger, CP dagger. And you can check, obviously, this satisfies correct commutation relation, this satisfies correct commutation relation. Every one of these commit with a second line. We have done that already in discussion, right? Now, what do you want to check? Well, now you can construct, you can check using a commutation relation of a Q with an A, which is completely encoded in here, right? In free theory limit. This is decomposable in terms of alpha, A and, oh, did I say A? Alpha. Who said A? Alpha. And if you replace this with A, you also have epsilon AB, A, same thing. No, alpha. I meant alpha, right? So this is literally replaceable with just alpha A, and then here alpha B. The exact same thing holds, right? This is linear. So now the task is basically to check, what kind of commutation relation B and C satisfies. So if you do it, you're gonna find, what do you think? What do you think? If you do it, here, C dagger, okay. It's an algebra you can do, but remember, what I was trying to do was to diagonalizing it. That algebra was not diagonalizing, right? Alpha basis, does not diagonalize Q. I wanted to diagonalizing it, so up to psi, you should find, I think, this. And then I'll explain. Let me check. Check psi. So at least you see that this BC basis, rather than the alpha 1, 2 basis, diagonalizes Q. Okay? Let's understand the meaning now. Physics and meaning of that. So that means if you had a B particle because you created it, under the Q, it stays to be B particle with charge +1. Right? If you had a C particle, under the action of a Q, you're still in the C particle. You didn't change it to something else with the minus sign. Okay? And then the other one should be understandable because in the field operator, so now, if you do this, remember, now, if you write down the field operator, you should have, if you combine this, something like e to the minus IPX, B plus IPX, C dagger, and vice versa. Okay? So what C dagger can do is basically the same as what B do, because there's the same minus sign. Okay? Or if you take a Hermitian conjugate, you get C and B dagger. So what B dagger sees, you get the same sign as in C. Okay? So therefore, the interpretation is that in this basis, right? In this basis where phi, at the risk of being redundant, let me just write it again. in this case is phi and phi dagger. The symmetry SO2 now acts as this thing has a C, e to the minus some alpha, and then dagger goes to e to the plus I alpha. So it diagonalizes. Okay? Any questions so far? If something is not clear, please let me know.
When you say the diagonalization, because the B is the operator, so if the Q is representing, of course it is impossible, but if it is represented to the matrix, then B is also perfect.
What do you mean matrix? Is it matrix? Oh, matrix. So by diagonalization, I mean more precisely that if I use a state created by the B and C, those states in the vector space will diagonalize the Q matrix.
Then we can systematically carry out such diagonalization
Yes, you can.
By taking some state cap to the equation.
Yeah.
And then diagonalize the state.
Absolutely, the same process. That's why I say that instead of actually trying to do actual matrix diagonalization and reinterpret in terms of field, I said that let me just write down the answer and just check it. Yes, but yes, exactly what you can do is true. Because this is like 1 minus 1. So you can diagonalize this, right? And if you do it, I'm saying this is the answer. Any other question? Okay. Now, since we discovered that starting from the two scalar field theory, which had SO2, forgetting about the reflection part, I can diagonalize that thing, and that sort of led us to start thinking about the complex field. So then you can say, what is Lagrangian written in terms of that? Let's do it. And now I'm just gonna quickly say, therefore, in principle, now we could have considered the Lagrangian that had a phi field, this, and then phi dagger phi. So this is one component of scalar, okay? There's a single die. And then you can ask the same question. So this is this thing is a 1 times 1, just literally one scalar valued, complex value field. So you can ask the exact same thing. So if I do some transformation, what types of U leaves this actually invariant? This is Lagrangian there. We could have asked the same thing. Okay, so then you will quickly find out that it is just number-wise, it is this condition, and you learn that it's nothing but this U1 phase. And that U1 phase was literally this. Okay? Okay, so that's U1 symmetry of complexity. Now, there's a little bit of an interesting story between these two, so let me actually mention that. So here, what I want to say a bit about is this SO2, or be careful about O2, versus here U1. This certainly captures SO2 correctly, right? So what about missing reflection part in this U1 picture? You could ask the same question. Is this literally identical, or there's something missing? So here, let's compare these two charts. Okay. So here, SO2 not diagonalized, right? Remember. So if A was epsilon AB, B. So that was not diagonalized. Here, the analog or counterpart of the SU2, which was U1, diagonalized. In a sense, it diagonalized SO2. So here, basically, it went into either dagger, into the minus or plus alpha dagger. So it's certainly diagonalized. On the other hand, we also talked about the missing piece, reflection. So what was that? 1 prime, 2 prime was 1 minus 1, 1, 2. So you notice here that reflection, reflection here is diagonalized, right? So with the phi 1 being eigenstate with the eigenvalue 1, phi 2 being eigenstate with the eigenvalue minus 1. So it's diagonalized. Here we can say, who is this? Very good. So you can actually quickly see, right? There's 1 over square root 2 of not this. Phi 1 plus I phi 2. And dagger is minus. So if you pick minus sign in front of the phi 2, you see that what it does is complex conjugation. Now, from U2 perspective, phi carry the charge, say, minus 1, and phi dagger carry the charge plus 1. Right? Because it picks up the minus 1 phase, and then the other one has a plus 1 phase. So you can say that this guy having a charge, if this is computing language, just look at this. Right? Particle created by B has a plus 1 charge. Particle created by C has a minus 1 charge. Or maybe I'm flipping the other two. Yes, I'm flipping the other two. Let me maximally confuse you. Particle, actually it's very consistent. Sorry, no, I'm not confusing you. Particle created by C has a charge minus 1. And that is actually consistent being the fact that the phi picking the minus phase, right? Actually, that's how I discussed, I guess. And then vice versa. But nevertheless, you make sure to check that this is consistent with the consistent interpretation with the word identity statement that I told you. Right? This Q phi is I, was that minus I? D phi, right? Okay. So therefore, let me reinterpret what reflection does in this complex language in terms of U1 charge. Okay, in terms of U1 charge, what it does is that if it flips what was sort of a particle with charge 1 or minus 1 into particle with charge plus 1. So it does flip the U1 charge. So the charge getting conjugated. This is called the charge conjugation, C. Okay, so that's sort of 2 languages. Now not hopefully missing any symmetry that presented. Okay, good. So now I'm gonna just introduce 2 more examples. Now it's quick because you are trained. Now you can just generalize. Once you understand simplest version, you can quickly generalize to more complex things. So another example that I want to talk about, was it the first example? Did I write EX1 or something? Yeah. EX? Without number. Very good. So just another EX. Okay. Because already I forget labeling this another as an example. That's fine. So let's consider n real scalars. So let me introduce the big phi 1. 5n. Okay? So here is the Lagrangian. Real, so I have a half. By the way, in case you have noticed it, in the kinetic term, for real I have a half, but in the complex I don't. Right? So you can double check. Why? Because there's a 1 over square root of 2. If you put it correctly, you get 1 over 2. And you might say, why 1 over 2? I don't like the 1 over 2. What about the pi? Right? And there was a reason for 1 over 2. You look scared. There's a reason for 1 over 2. I was trying to derive Lagrangian. By knowing the fact that I wanted to satisfy a Klein-Gordon equation without any unnecessary factors, once I derive all the Lagrangian equation out of this. And then 1 over 2 was put it in, so that free streamline machinery landed on this beautiful Klein-Gordon without other unnecessary factors. Okay? So anyway, so I can write this as transpose. I'm dropping again the vector notation. Oh, ooh. There you go. Okay. And we can ask the same question. So what types of a transformation leave this invariant, right? If you do it, you will literally get the same equation, except the fact that now you won't impose that this is actually one n-dimensional unit matrix, right? So this theory will have therefore a symmetry of what? A? O? Okay. O and symmetry. And it plays important role in physics, O and mod. Then people even think about what if I send n to infinity? Actually, what does it even mean? Last example of the day. So let's consider now n complex scalar. Okay, so the same thing. But the only thing changes is that I don't see have dagger So again, if you do the same thing, now I'm gonna send this to you, and you should find out that the condition is this, is equal to n-dimensional identity. And this is known as what? What? Yes. Now this thing has UN symmetry. Another very important example in physics. N people, as you have, now you'd expect us to consider sending n to infinity and ask questions. Okay? Anyway, so I think that's proper time to stop. And next time we will go through 3 important discrete symmetries after Thanksgiving. It's known as the C. I've already talked a little bit about it. P and T. Okay? So that's all we're going to discuss after Thanksgiving break. I hope you will have a great Thanksgiving break. That's all for today.